Hey you guys, welcome back to this neat code along. So today we're going to continue the speciation. Now where we left off is we were in the neat utilities function and we just got done getting the disjoint and access genes. So if we look at our what we're trying to get is the compatibility distance for our speciation. So when we look at our function for the compatibility distance, we need to get our the number of access genes, the number of disjoint genes, and we have to get the average weight differences of matching genes. So right now we're going to figure out how to get the average weight differences of matching genes, and then we're going to get this compatibility distance, and then we're going to implement speciation in our environment after we have all the setup done for this neat stuff. Okay, let's get started then. Now I have the project open right here. Got the code open. And we'll get started. Well, 1 second. Now, first let's erase this right here. We don't need this anymore. There we go. And now we have to kind of change the way our function is returning. So right now we return a integer array which holds our disjoint and access, but we want to return a var array because we want to be able to pass in a float as well. We want to return integers and floats. This is so easy in Python, but C# I don't really know how to do it. But we're going to have to figure that out real quick. No returning. What are we in C#? I don't want to pass it. Yeah, that's what I thought. Could we do list var? Will it let us? Let's go down this. Right here. This should be what we need. So I'm gonna copy this. Well, let's just type it. So tuple, I have an int and a float. That's what's going to be returned. And then down here, instead of this now, we're going to do, actually, right here, and do that out as well. Return tuple dot create. Make sure create disjoint access, and we're going to create a new variable called average weight difference. It's going to be a float, we'll call it AVG, our average weight difference, AWD, 0. Okay. And here we're going to pass in AWD. Actually, let's just, we'll do it like that. There we go. Now this should have our that in there. I think now we don't need to do that. Now we could just, if it's that easy, I'm just not very good at coding, clearly. So we'll get rid of that. See if it automatically unpacks. And this is actually similar to Python. And then, yeah, that's perfect. So I think that worked right here. The way, oh, that's so much simpler than what it used to be. And I can prove that for the record. Now in C#7, it's like this. That's all I'm saying. All I'm saying. Before it was more difficult to do. Okay, so go back to the code. So now that we have it this way, we have to change where we're calling this function. Make sure that it's being returned into these values. So we go to our neat genetic manager and we go down to our stored population, and we actually call this right here, right? So now we have this. I'm assuming is going to be, and I do not know for sure, int float blah blah. No, I get it. So it's going to be blah, but we're going to do int float. Maybe. Okay, all errors fixed, but I don't know what that's going to print. So let's press play. We'll up the time scale. Wait for print. Nice. 1 0. And now how do I access the individual values? Tuple. I think tuples are set up in item 1 and item 2. All right, let's try that. Yep, so that does it, which is such a weird way to access data. Item 1, item 2, I don't know. Okay, so we have item 1, item 2, item 3. So now we'll at least be able to see what's being returned right here. And then in here, I see that there's an extra print statement. We don't need that for now. And all right, we're all set up to start getting the average weight difference. And one interesting thing is we could do this in 2 different ways. Now we could create a function that gets our average weight difference, and within that function, we can loop through the connection genes and the connection genes for the first parent and the connection genes for the second parent, and we can compare to see which ones are matching and get the average weight difference that way. But that would involve 2 extra loops, and we already have within this function right here, we already have the loops we need for the comparison, right? Our comparison is happening right here. So we don't need to add an extra 2 loops, which will make this whole program kind of slow. It'll increase our runtime. We don't and we want to kind of keep as little extra computation as we need. When it comes to these loops, if we're looping through the whole genetic if we're looping through the whole list of the genome, right, then our runtime's already like the amount of time it takes to loop through one genome, and then within that loop we loop through the second genome, so the amount of time it takes to loop through that genome as well. But we're doing it exponentially, so we're already actually not that good on runtime, so we should just kind of optimize it. Now the way we're going to do it might be a little confusing, so it's not as simple as the first way, but it's a better way to do it, so that's why we're going to do it that way. And let's get started. First of all, so the average weight difference, what are we even talking about, right? It's important to cover that. The average weight difference is going to be, and can't even find my screen. Okay. The average weight difference is basically, and this paper doesn't have a good explanation at all, but the average weight difference is the average difference between the matching weights, including the disabled genes. So if we're comparing 2 genes, right, we have to make sure the innovation number is the same, and that the two we have to make sure that the innovation number is the same and that the edges are the same, right? That the input node matches the input node and the output node matches the output node, which is exactly what we're doing right here in this loop. And we're returning 0 if it is matching, right? If it is the same, and 1 if it isn't. Now, what we can do right here then is create an if statement that checks. If it's 1, we add 1 to disjoint, and if it's 0, then we can add to the average weight difference, and at the end we'll divide the average weight difference by the number of matching pairs of genomes, which is what actually will get our average. If we don't divide by the number of pairs, then it's just addition of the differences. So, that all being said, there's one more thing. Oh yeah, okay. So another reason why this works really well for us is that we have this separated. We have a breakpoint, and so this only runs for genes that are potentially matching. So anything past the breakpoint will go into access, but we know for a fact that access cannot be matching, you know, because they're extras. So we don't even need to loop when we don't even need to loop to the biggest array. We need to loop through the smallest one, which is what the disjoint does. This is another like cool computation thing that helps make sure that we are not slowing down our program. So let's just get started on this. Now that I have this, let's comment this out and we'll create a if statement, and we'll do if is disjoint second cons, and it's going to be the same stuff we're passing, con dot num dot first cons comma first cons equals 0. Then this we know is, well, we'll do equals 1, and we know is disjoint equals true. No, let's not do it, because then I'll think it's actual code. Is disjoint is true. And so since is disjoint is true, we will do disjoint plus equals 1. So we don't have to call this function again. So it's not just like we're copying this into here, and we'll be calling the function way too many times. We could just add 1. And then else is disjoint is false, meaning genes are matching. And now we calculate the average weight difference. So I need to see in C# how to get the absolute value. Math.abs. So let's do that right here. Math.abs. So we're going to get the absolute value. Oh, this might be actually more difficult than I thought. We also need to get the weight of the whatever's being passed here. So we know that we know the innovation number of is disjoint, but we don't have the weight difference. Let's go down to our, what we need to get is the weights for these matched, so compcon and basecon. We need to get the weight for that. So I think now we will have to change the way this function is also returning. We need to return those weights. I'm just thinking about exactly how we're going to do this with the returning of the weights. So anytime 1 is returned, we know that it's disjoint, so we don't need to return the weight. We only really need to return the weights here. But we could do it in the same kind of way we had done it before. We did multiple variables up there. We could do this, and we'll pass an int. That int will still be the same. That will be our representation of true and false, even though we could just pass a float now. I mean, not a float, a bool. Let's do that. We'll pass a boolean for whether it's disjoint or not, and then we'll pass in a float for the first weight and then float for the second weight. All right. So now we got that, we can do tuple. No, we don't even need to do that anymore. We'll do this. And what we'll do is 0 was false. It is not disjoint. Yeah, so false. And then we're going to pass in compcon. Actually, this should be the first one, the base connection, right? So we're going to pass in, even though it doesn't matter at all. But we're going to pass in base con dot weight. And we're going to pass in compcon dot weight. Perfect. And now we're going to pass in true. And then nothing and nothing. And we're going to pass in true and then null and null. And let me just make sure about the errors. Great. This is on line 52. Ah. Okay. Float is not nullable. So then instead of passing null, we'll pass zeros. It doesn't really matter what we're passing here. That is true. Okay, so it says no overload. A print takes 3 arguments, so it's in the neat genetic manager where that's happening. So neat genetic manager where we add the sort population, the print. We just do plus that, and then we copy this right here. We add that right here as well. Okay, and finally, this cannot convert the tuple to int. So that's going to be in our neat utilities. And that is, if we scroll up to our get disjoint and access function, it's going to be right here, because we're checking to see it's 1 when it should be the item 1 equals false. Oh, equals true. But if it equals true, we add 1, and if it's false, we have the 0. Let's see if this works. Perfect. And now we are kind of in a better place to solve this problem. So we have disjoint plus equals 1. That's good. And now we do mat for the AWD. We'll do AWD plus equals math dot absolute value of, I have to store this, don't I? Okay, so we're going to create a new variable of type bool float and call it is matching equals is disjoint. This actually should be is not matching, since we have a true. So is not matching equals is disjoint well, equals this function right here. So we'll just copy it over, not including the end part. Okay. And now we'll take this and put it right here. Is not matching. That should do that. Right here. Now that we have that, we can do is not matching dot item 2. So that's the weight of the first matching connection, right? Of the base connection that is matching. And subtract that from is not matching dot item 3. And then that gets the connection for the second matching gene. Alright, so that will get our kind of total. But we also need to now get a count for our, so that we could divide by the number of matchings, right? We have this here, and now we need another integer, int matching count equals 0. And then right here, matching count plus equals 1. So, you know, as we get the matching, we're just counting up. And now we have all of our values that we need to calculate this average weight difference, this compatibility distance. But now we get the average, and obviously one annoying thing about averages, as always, is that you can't divide by 0. So we'll do a if is matching count is greater than 0, we'll do AWD equals AWD divided by matching count. And if it doesn't equal 0, that means that we didn't have any matching, right? So nothing got added to AWD, and we'll be at 0 right here. But there's a problem with this. Like, there's a problem with everything. If there is no matching, interesting. Fix that right here. Let's make this a capital D. There is a problem with this. Actually, the problem is that, let's say we have a large difference, right? Our average will actually be really high, because whenever we subtract, we will get large values from the subtraction. Will it be high? It's kind of gonna depends on how much of a difference it is. But when we pass in 0, we're saying that it's exactly the same. We're saying that there's not a lot of weight difference. It's an interesting concept. Hold up. Let me look at the paper. The number of axes goes up. As the difference increases between these kind of genes, the number of disjoint goes up and the number of axis goes up. So our compatibility distance is actually getting bigger. Like, if it's large, it's a large value, then that means that the two things are very different. However, when we're passing in 0, right, when we say that there is no weights matching, it means that the network is extremely different, right? I mean, there's nothing matching. So when we pass in 0 for nothing matching, but our access and our disjoints would be extremely up. Well, specifically our access probably. Well, access and disjoint probably be extremely high. The weight doesn't really, this maximum weight difference, the way we're doing it, doesn't really, it's not really a distance. If it was a distance, then if the network was perfectly the same, well, if the weights were perfectly the same for all the matchings, then it would be 0. And if the weights were completely different, it would probably reach a maximum like distance of 1 that represents like as different as can be. So we might also like we might change the way we calculate this as well. But right now, I think we'll be fine with the way it is. Yeah, we'll be good like this. It's fine. Because our access and our disjoint will still kind of, you know, if this will be 0, these will be extremely high. And our weight matching doesn't really have, because we have a constant here, so we can change the how much effect it has. It's actually not going to have that much effect on this function. So let's continue on. That's pretty cool. So we got the weight difference. It should be that right there. Math doesn't exist. Didn't I use that in what the heck? I believe we used math in our neat network. And why does math exist here but not in? Imports are exactly the same. And math F. I think it's let me find the word. What did they say? What was the error? I believe it's the math came system.collection. Okay. I always thought math came with system.collections. Still didn't fix that. This is exactly what I used. Oh no, I didn't. I just wrote math. Okay. Math does not contain. And actually what I'm going to do is let's not import system, and we'll just use system.math. Math. Okay, and now it says math does not contain a definition for ABS. Let's go back to our thing. Oh, because I know why. Back here, the A have to be capital. There we go. Perfect. Now we're good to go. We got the average weight difference, and we got all the stuff we need for our disjoint axis and average weight difference. Let's print and see how it looks. Let's change this up to 30. We need a little bit more complex networks that will have similar matching edges. Ow. Alright, so there's our average weight difference. This is actually, what this is saying right here, let's pause this. What this is saying right here is that the two top genes are very similar because, one, they have no disjoint edges. I mean, they have no disjoint genes, meaning that everything within the breakpoint is matching, and they have no axis, meaning they have no genes past the breakpoint, meaning all genes within the two that we're comparing, all of the edges are matching. And so, since the edges are matching, we're calculating this average weight difference. And we also see that this, when this one was done, right, when this function was called, the two had a smaller weight difference than this, meaning these two were probably more similar. Now, I can see this mathematically, but if you guys want to see it visually, we're going to have to do the visualization of the neat network. When we click on the fish, its neural network displays in our simulation. That's going to be done after speciation. So let's finish our speciation and then we'll do that. But it is working fine. We can see that when edges and weights are matching, we're getting an average weight distance, and we know that distance is right because of the math of it. We're adding the differences between the matching weights and then taking the average of them. It's actually pretty cool to see. Well, but now let's calculate the compatibility distance, which is the key part of our speciation. Before that, we'll create another function called get compatibility distance. So pub static, and it's going to return a float. Perfect. And what we're going to pass it is exactly this right here, right? Actually, what we'll pass it is the actual genomes. So it's going to be neat genome first genome, and then neat genome second genome. Cool? Cool. And the first genome, second genome, those are the two we're going to pass it. But we also need to pass it the constants that we're going to use for this. So C1 float C2 float C3. All right. So now we can get started. And the way we do this is we're going to do a tuple int float, and we're going to call it disjoint access AWD equals get disjoint access, and we're going to pass it first genome dot connection genes, and then second genome dot connection con genes. All right, and that will get us, this is actually exactly what we're calling here without neat utilities, right? And actually now we can go into our neat genetic manager, and we won't test it here for now. We're going to test the actual function. Excuse me, I'm still a little sick. So we'll save this. Go to here. Now that we have this, okay, we'll calculate the compatibility distance, which is going to be a float. Compatibility comp dis equals, and so our, let me just, I've seen this so many times, but I tend to double check things like 100 times. So n was the number of the length of the number of access, no, of the smallest gene, I think, but let me make sure. Oh, I'm like squinting at this, I could just zoom in. So n is the number of genes in the larger genome. So we're gonna have to get our n. We'll do that by, so n is going to be an integer, int n equals, we want to get the, this is going to be interesting. So if n equals first genome dot con genes dot count is greater than or equal to second genome dot con genes dot count, then if it's true, we want to return the first genes count. And if it's not true, if it's false, we pass in the second genome dot con genes dot count. And that should get us the biggest one. But we're going to have to do a print to test this. And let's remove our any print that we have in here, because this function is done. Perfect. All good. And now let's come back to here. Print. Now we're going to print the count of the first genome. Print the count of the second genome, and I know we can't use comma. And genome.count, and now we do n, whatever our n is. N should be the biggest 1. And so to call this function, we'll go into our neat genetic manager. And we're going to do neat utilities equals not all code paths will return a value right now. Return 0 for now. Here. Need comp dis equals not get compatibility distance, and we're going to pass in all neat networks 0 dot my genome, and then all neat networks 1 dot my genome. Okay. Oh yeah. So in our neat genetic manager, we go up to the top and we'll create public C1, C2, C3, and that will be int. Oh, those are going to be floats. See if that works. Okay. And so open this up and let's go to our neat G manager. Man, there should be an easy way to do this, and I just probably don't know how. And then we're gonna pass in C1, C2, C3 for the constants. There we go. And here's our C1, C2, C3, and so on. So we're gonna keep 1, 1, 1, A2 to 1. Okay. See that print. Yeah, it looks good. So this should be our biggest value, and this is our biggest value, so yeah, it's working. Go back to our neat utilities. We don't need this print anymore. We have n. Now we can get our compatibility distance. This equals, our function is C1 times won't matter anyways, but C1 times item 1. So item 1 is our disjoint, right? But that isn't even right for our function. It should be item 2. But this is going to be a little hard to visualize, so I'm going to create, I know this, but It's not as good for memory, but I'm going to create the values for these. So int disjoint equals disjoint access dot item 1 int access equals disjoint access dot item 2, and then float joint access equals and then float AWD equals joint access dot item 3. There we go. We have our 3 values right here, and I think actually I could have probably just done this joint here and then comma access, because that's actually what tuple unpacking is, but whatever. I kind of want to try that now. Whatever. I have bad tendencies. I'm sorry. Don't do what I'm doing yet, or you can. I just want to see if this works. And I'm just gonna comment all this real quick. Yeah, okay, can't do that. Good. Just gonna backspace, back, Control Z, Control Z until I'm back to here. And then I'm gonna Control Z some more until I'm back to here. Okay? So we're back to where we started. And now we can change this right here. This will be access, right? Because if we look here, access. So the exact function is actually disjoint access divided by n plus and same thing we're going to do C2 though, and then times disjoint, right? So we have our inner, or our top part, numerator, and divide that by n. And this actually doesn't matter if you didn't add these, right? Your order of operations will take care of it still, because you'll do C1 times access, then do the division, and then you'll do that for here as well, and the next one, and then you'll do the addition. But just to be clean, this is actually how it's supposed to be written. And now finally, we have C3 times AWD, and that is Control Z to bring that back. I press Control X to cut the line. But so that is our whole compatibility distance right there. Yep, C3 times AWD. Awesome. And now let's do return comp dis. And so now this should be getting our compatibility distance perfectly, and we'll go into our neat genetic manager and we'll print comp dis. Where do I have? This should be, well, let's do disjoint, and we'll change this right here to disjoint with a lowercase j. And there we go. Let's press play, and let's up the time scale to 20. We had a high difference here, a smaller difference here. And now they all spawned from the same parent, so we should have small differences. These fish are doing too good. Alright, so we have 59, 58. So we're seeing that as time is going by, we're getting larger and larger values because more mutation is happening, causing the two top species to kind of shift apart over time. But as we're getting, but we'll sometimes see it go down because obviously we do need the best species to be somewhat similar, and the best species will be the top two. Well, the best species will be the top. But you see, like right now, we only have one lone guy that is doing good, so we'll see a large difference. But if we have two creatures that are doing good similarly, they're probably going to have a smaller distance. So I'm trying to wait till we see an example of that. Make sure that the hypothesis. Man, we're not even getting past 300, but we have gotten past it before. I think this is, we're just getting unlucky. I'm gonna pause this and run it again. You see, the compatibility is very small right now. Three hundred seems to be such a difficult spot for them to get over. Well, you guys have seen it go up to like 1,000. We didn't really change anything when it came to training. Not yet, anyways. All right, somebody finally did it. And now they're all dying again. Okay, these two should be similar. Oh, they got saved, so we didn't. Okay, so training is working fine. As you guys can see, it's going up, and our compatibility distance is gotten. So we're done with getting compatibility distance. That's great. Now we need to begin working on implementing compatibility distance in this simulation. So next we're going to create a class for the species, and then we're going to begin giving our fish the different colors. So I'm going to take a little break again. We're finishing at a good part, and then we'll continue it on next, and hopefully in the next video this should be over with. Thank you guys for watching. I really appreciate it, and please leave a comment below letting me know if you guys like these videos. It really helps me and motivates me to make more videos. The last two videos I added, I admit was not polished, but not a lot of views on it, and it's making me think maybe this is starting to become like one of those tutorials that never end, and then people stop watching it, you know. And it does feel that way on my end too, but we are coming near an end for this. So after speciation, we just need to do the visualization and then the crossover if people really want to see it. But what I'm hoping to do is, actually, this project was a little too complex to just showcase speciation. You know, like the light chaser problem is not the best showcase for this. I think a better one would be like a self-driving car or something, right? So maybe we'll reboot this series with in a tutorial format for like a self-driving car in Unity. And I don't know, we'll see. But just leave comments so, you know, I'll see if there's interest in something or not. Thank you guys. Goodbye.